Okay, so you can pick up your third homework during the break. And if you haven't handed in your fourth homework, it's now your time. Your fifth homework is already not the class, so, and that is due for next Tuesday, not for Friday. Now let's have a short review of what we have been discussing this week. We have been mainly studying about the dipole moments and the polarization of a medium. In the beginning of the week, if you remember, we first considered a neutral atom. If you consider a neutral atom, put it in an electric field, the negative and positive charges will be displaced slightly in opposite directions, and hence creating a dipole moment. Or if you have an atom or a molecule which already has a dipole moment, we had seen that a dipole moment, if you put it in an electric field, it will feel a torque, try to align it in the direction of the electric field. So whichever the mechanism is, if you take any material which is made up of atoms and molecules, if you put it in an electric field, then that electric field will create a net dipole moment in the material. And if the density of this dipole moment, your material need not be homogeneous, it might have different properties at different points. So the dipole moment of the atoms at different parts will be different. So we define this concept of the dipole moment density, which was basically, we denoted it by a large polarization P. We called it the dipole moment density, the polarization of the medium, and it was defined as, if you just consider very small volume around the point R, then calculate the total dipole moment in that volume. Let's call it delta P, and the volume is delta V. This is how we define the polarization of the medium, or the dipole moment density. This was the definition we made, and then we asked the question, okay, so we have this material, we put it in an electric field, it will create a polarization in the medium, and hence this polarization will itself create an electric field, because we had also seen that if we have this polarization, if a medium is polarized, effectively we can describe this medium as a medium that has some charge distribution, and the charge density in the volume was nothing but the divergence of this polarization, and on the surface of the material it corresponds to a surface charge density given by this scalar product, where this n is the perpendicular direction to our surface. So if you have a polarized medium, if the polarization is non-zero, you can model the effects of this polarization as a volume charge density, which we call the rho b for the charge density corresponding to bound charges, and also the surface charge density, basically the surface charge density created by the bound charges in the medium. And then we asked the question, so since the polarization corresponds to a certain charge density, what is the electric field created by this polarization? So you have your medium, you put it in an electric field, the medium becomes polarized, there's a non-zero polarization in your material, and this polarization itself creates an additional electric field. So the total electric field will be the external electric field plus the electric field created by this polarization. Now we first asked the question, what is the electric field created by this polarization? And as an example, we had started looking at the problem of a sphere with a uniform polarization. Let's say in the z direction. And now we said that, okay, since this is uniform, the bound volume charge density, the charge density inside our medium, was given by the divergence of this polarization. Since it's constant, it is just 0. And now we have the surface charge density, which is just P dot n. For a sphere, n is nothing but the radius vector if you choose your origin. This is z. This is x, y, and z. N is nothing but the radial unit vector. And this is p times cosine theta. So we have such a surface charge density And now the question is, what is the electric field created by this surface charge density? And of course, once we know the charge density, we can put it in the expression of the electric field and take our integral expression, take the integral, and we can obtain what the electric field is. But rather than having this brute force, let's say, computation, what we were studying is we were studying a related problem. You have one sphere, and you take another identical sphere and displace them slightly. One of them has a charge density, let's say, minus lambda. The other one has a volume charge density plus lambda. Then the question is, what is the electric field here in the intersection? In this region, there is no charge density because in one of them we have the minus charge lambda, in the other one we have the exactly equal in magnitude but positive charge density, so the sum is 0 in this region. What is the electric field in this intermediate region? And if you remember, what we had shown was in the intermediate region, well, let's just review it. We said that, okay, first let's look at this problem of the uniformly charged sphere with volume charge density lambda. We are looking at the electric field at this point. Inside our volume, we had considered this Gauss surface. Then the electric field inside that volume is in the radial direction because of the symmetry. And the electric field is 1 over 4 pi r squared. Now let me erase that. 1 over 4 pi epsilon 0 times the total charge within this volume. Well, the total charge within that volume is nothing but 4 over 3 pi r cubed times lambda divided by the distance from the center squared. This was our electric field at that point r. And then if you just make the simplifications, this just becomes 4 pi's will cancel this 4 pi. We have 1 over 3 epsilon 0, lambda over 3 epsilon 0. This will cancel 2 of them, r in the r hat direction, or this is lambda over 3 epsilon 0 in the r hat direction. This is the electric field on a point inside the sphere that has a uniform surface volume charge density lambda. Now, in this problem of overlapping spheres, we basically have, let's say, this is the center of one, this is the center of the other one. And we want to find the electric field at this point. Let's just define these vectors. This is R1 vector. Let me call this one the R2 vector. So the total electric field will be the electric field created by the negatively charged sphere, which is minus lambda over 3 epsilon 0 R1, plus the electric field created by the positively charged sphere, which is lambda over 3 epsilon 0 times R2. If we just combine them, this is lambda over 3 epsilon 0 R2 minus R1. Or if you look at that diagram, R2 minus R1 is nothing but this vector. So this is equal to the electric field is lambda over 3 epsilon 0 times T. It is a uniform electric field. So although the charge distribution is a non-trivial charge distribution, we have a crescent-shaped charge distribution over here, another one over here. The shapes are quite complicated. Here we don't have any charge. Nevertheless, the electric field inside is uniform. It doesn't depend on D is just a constant vector, lambda is just constant. And we can also write this in a different form. Let's say our spheres have a radius r. This is equal to 4 over 3 pi r cubed lambda divided by 3 epsilon 0 4 over 3 pi r cubed in the d direction. Well, the reason, what I did was I just multiplied by 4 over 3 pi r cubed and divided by 4 over 3 pi r cubed. The reason why I did this is that this is the volume of my sphere. Lambda is the charge density, that is charge per unit volume. If you multiply this with the volume, this is the total charge of one of the spheres. This is equal to QD divided by 4 pi epsilon 0 r cubed. But you see, we have these two spheres. One is plus q charge, the other one is minus q charge. Their centers are slightly displaced. So we have basically a dipole system over here. And the total charge times d is nothing but the total dipole moment of the system. So this is P over, or let me write it, still keep it in the other form, 3 epsilon 0 4 over 3 pi r cubed. So that's small p is the total dipole moment. I divide it by the volume. That is what we call the polarization. So in this system at least, the electric field in the overlapping region of these two spheres is given by the polarization over 3 epsilon 0. Now, still we don't have the relation of this system with the real system that we are actually interested in. You see, what we are actually interested in is not two overlapping spheres displaced by a distance d. We are interested in a single sphere with a surface charge density given by p times cosine theta. So let's see if we can relate these two systems. So this is the system for which the solution we know. Our original system is the one for which d goes to 0. So if d goes to 0, we have a single charge density, single sphere. But then the problem is if d goes to 0, let's say this was minus lambda, this was plus lambda, the total charge of the polarization also goes to 0 because polarization is charge times d. So to keep the polarization finite, we have to somehow set lambda to infinity in such a way that q times d should be constant. You see, q times d or lambda times d is, you see here the polarization is equal to lambda times d. So if we set the magnitude of d vector to 0, we still would like to keep the polarization constant. So lambda times d should be equal to p constant. This is the limit that we will be considering. We will take d to 0, lambda to infinity in such a way that their product is constant. Then what will be the surface density of this system? That's our next problem. Now, to find the surface density, let's just imagine some horizontal lines. Horizontal planes, let's say. And let's just take this part. What is the total charge of that segment? So that will be my question. What is the charge of that segment? Okay, first of all, what is the width of that segment? Okay, so let me draw it, enlarging it. This is one sphere. I have an identical second sphere. Well, of course, I will be taking the limit that d goes to 0. That thickness will eventually go to 0. Now, I would like to determine the charge density, surface charge density. Now, let's see. This is the, well, now both of the centers are almost overlapping. How do we define the surface charge density? You just take an area on the surface, and the total charge of that area is equal to the surface charge density times the area. Now, of course, at this limit, it's not really a surface yet, it's a volume. But in the limit that d goes to 0, it becomes a surface. So first I have to identify a surface, then define a volume corresponding to that surface, and then calculate delta Q for that volume. When I take the limit as d goes to 0, that volume becomes a surface. And then I know what the area is, I know what delta Q is, I can talk about the surface charge density. That's the strategy. Now, of course, the problem here is we have to somehow, okay, I'm moving this sphere. Okay, so the left sphere is fixed, the right sphere I'm just slowly moving so that eventually I have the d equal to 0. So I have to first take an area. So this is my area over here. Just imagine this is a three-dimensional object, not just a circle. So that 2 dots, that small arc is actually some area. So I have this very small area. Over there. Now, if you want, we can consider this part. So this direction. So how much charge do I see in that area? So that's my question. How much charge is in this region? How much charge is there? Well, to determine that charge, I have to somehow identify the volume. What is the volume between these two spheres? Of course, it depends on the angle. So that is what we hope. We hope to get sigma should be proportional to cosine theta somehow. That is what our aim is. So we are, this is our angle theta. So what do you propose? dq, d theta. So this is dA, or is this dq? Remember, I'm interested in the charge, and I want to divide it eventually by A. Now, my proposal was this one. Rather than imagining such an area, I can imagine such an area. I divide it by horizontal, I take horizontal slices. So what do I have over there? I have such a slice. I have such an area. And then I have this vector over here, which is normal to this one. And let's say this angle over here, or let me call this angle phi. This angle is phi. Now, first of all, what is the thickness of this region? That is the first thing we have to answer. How can I calculate the thickness? I don't know the answer, by the way. And the answer should be lambda times d times cosine theta times a. Should be. Or delta a. So that when I divide by delta a, I get lambda d times cosine theta, the total charge, and lambda d goes to 0, lambda goes to infinity, lambda d becomes the total polarization, which is my previous system with a surface charge density given by p times the polarization. So this is the answer I want. Is it the correct answer? Or how to see that it is the correct answer? Let's try to calculate the thickness. You see, this is also perpendicular, and this is our d. This is our phi. Do you agree? So you see, what are these shapes? This is one sphere. This is another sphere with a shifted center. They are the same shape, basically. If you draw the radial lines to both of them, the perpendicular line will go to the center of the first sphere, and the perpendicular line will go to the center of the other sphere. And these angles, since they are identical systems, these angles basically are the same.
Daralıyor. İkisi arasındaki mesafe sıfırlanıyor.
I'm a bad painter. Does this kind of help?
Sadece x merkezi birleştiren eksen üzerinde geçer değil mi? Yani azimut angle değiştirdiğim zaman durum ortadan kalkmayacak. Polar koordinatlardaki pi üzerinde değişik yaptığım zaman. Ya bu küreleri tabii nasıl ettik şu an cross section'a bakıyor.
That distance is actually d. Imagine what we are doing. I have this sphere, I'm just shifting it. This point over here just moves by a distance d. Now we have this area A. This is my area A. This is the distance D. The shape is more or less like this. To get the volume, well, let's say this angle is theta prime. The volume is nothing but h times A. But h is nothing but d times cosine theta prime. Well, you see this line is perpendicular to A. So this line is basically perpendicular to A. And it makes an angle phi with the horizontal. So theta prime is actually phi, which is pi minus theta. So delta V is equal to A times D times cosine pi minus theta, A times D times cosine theta. This is the volume of that very small segment. The charge, A times D times, well, plus or minus lambda, times cosine theta. Well, in fact, cosine theta, if you just allow cosine theta to be an angle between 0 and 180, it takes care of this plus and minus sign. I don't need to worry about that plus or minus sign. This is the total charge corresponding to a solid angle which corresponds to the area A. And the surface charge density is delta Q over A, which is d lambda cosine theta, and in the limit it goes to p cosine theta. Now, the somehow complicated part is how to relate lambda to the surface charge density. And it just is kind of eliminated if you just take a very small volume over here, which has an area A, and then once you realize that the volume of this part is nothing but A times D times area times the shift D, which is basically this shift also, times cosine theta, then the surface charge density is p cosine theta. So now what do we know? In this system, where we have, let's say, positive charges over here, negative charges over here, where the surface charge density is p times cosine theta, this system we can treat as the limiting case of this system. But in this system, we had seen that the electric field is given by the polarization divided by 3 epsilon 0. Well, just one change. You see, D vector is pointing from positive charge to the negative charge. That's how I define the D vector over there. So here I have a minus sign because the polarization vector is defined from the minus charge to the positive charge. The electric field is pointing in the opposite direction. So here I have a minus sign. So this is the electric field created by a uniformly polarized sphere inside our sphere. So if we have a uniform polarization, it creates a uniform electric field in the opposite direction. This is the electric field created. So if we if we have a uniform polarization density, it corresponds to a surface charge density given by this for a sphere. Now, rather than writing this charge density in an integral and trying to evaluate the integral, we made an analogy. Well, if you are not following the calculations, don't worry that much. The trick is basically the realization that if you have such shifted spheres, this problem becomes a sphere with surface charge density in the limit that these two spheres overlap. So once they overlap, well, of course, there are some technical details like taking that limit. If they overlap, there won't be any charge left unless you first set lambda to infinity and such that the product is 0. Or in a sense, you can think that they almost overlap with a very thin skin, which is negatively charged on one side and positively charged on the other side. So this problem of a uniformly polarized sphere is actually exactly the same thing as these shifted spheres. Well, from a physical point of view, they are also exactly the same, because a uniform polarization you create by an external electric field, and what an external electric field does is it just shifts the negative charges to one direction and positive charges on the other direction. That is what the electric field will do to polarize the medium. It's exactly this problem. And then, of course, there were certain technical details to prove that they were formally identical. If you are not following, just skip them. And so once you show that these two problems are identical, keeping in mind that you should take the limits with this property, that lambda should go to 0, lambda should go to infinity, d should go to 0, and such that lambda times d is the magnitude of the polarization density, or the polarization. These two problems are identical. The electric field created by this system is trivial. Now, if you are out of this system, not inside by just at a point outside, well, for an outside observer, it doesn't see these spheres. The spheres just act like point charges at their centers. So we have a plus q charge at this point, a minus q charge at this point. Then we take the limit that d goes to infinity, d goes to 0, q goes to infinity. It creates a dipole, a finite dipole. So for an outside observer, it's a pure dipole, this uniformly polarized sphere. So we already know what the potential is, at least. This is inside. Outside, V is equal to the total polarization of the total dipole moment of this system is 4 over 3 pi r cubed times p dot r hat divided by r squared 1 over 4 pi epsilon 0. This is the potential created by this uniformly polarized system outside my sphere.
Potential.
This is the potential. Just take the gradient. It gives you the electric field. Because this is the potential of a dipole, not of a monopole. And if you would plot the electric field lines, this is the dipole we have. Let's say this is the P. The electric field inside, well, P is in this direction. The electric field inside is in the opposite direction to P. It is also uniform. This is inside. Outside, it just acts like a dipole. Outside, the dipole creates electric fields of this form. Is it wrong? Why? Remember, the electric field lines, they just start from positive charges, they end at negative charges. They don't form closed loops. So this side is positively charged, This side is negatively charged. So the electric field at the positive charge, some of them go through the medium matter, some of them go out of the matter, and they go to the negative charge. An electric field line is discontinuous on the surface, but that's also expected because the electric field line should be discontinuous on a surface that has a surface charge density. Any questions?
Şimdi şu dışarıdaki elektrik fizi için şunun içine mi bakacağız yani?
Yes. It should have this form.
Eksi işareti ne?
Which minus sign?
Eşittir eksi.
Everything should be included over there. When you take the gradient, it should be this one. Well, I might have forgotten some factors, but it has this form. Now we can calculate the total electric field. Now let's go back to the electric field. Okay, this is the polarization, the electric field created by the polarization. If we have a total electric field, we can obtain it through these two equations. Curl of the electric field is always zero whether you are in math or not. Divergence of the electric field, remember it was 1 over epsilon 0, rho over epsilon 0. Now, in the material, we kind of separated this rho into two parts. One, the charge that we place, which we call the rho free. And then there is the other electric field, which is created due to this polarization of the medium, which, I mean, they are not charges that are free to move. We are not free to put them or take them away. They are there. But once you create an electric field, they will form. And that we call rho b. So this is the divergence of the electric field. This is the curl of the electric field. Of course, if we know rho b, then we can just solve this equation just as we did before. The total electric field is just the integral over the total charge distribution. But most of the time, we just calculate rho b from the knowledge of the electric field. So we don't really a priori know what rho b is. So we would rather obtain an expression which doesn't refer to this bound charge explicitly. But let's make one observation. We had said that rho b is equal to minus the divergence of p, the polarization. We can put it over there. So epsilon 0 times the divergence of E. This is equal to rho free plus minus the divergence of polarization. Or the divergence of epsilon 0 E plus this polarization is equal to rho free. Now, this combination is what we usually call the displacement field. This is the definition. And the divergence of this displacement field is equal to rho free. This is kind of the equation that we were looking for. It only contains the free charge. But of course, I mean, there is no free lunch, let's say. We gain one thing. This equation doesn't refer to bound charges anymore, but we have what we call this displacement field. Those are the charges that we are putting in the system. For example, what we will do is, as an example, take this material, inside put some charge. So that is what we control. We put charges there. But once we put charges in our material, it will create an electric field. This electric field will polarize the medium, and hence inside our material it will create some charge distribution. That is what we call rho bound. It is created by the displacement or the orientation of these bound charges. That's not something we control. That's something we need to calculate. So any questions before you go for a break? Now we will pick up from here in the next hour. Any questions before you go? No, I mean, it can depend on anything. It depends on you. How do you want to create a charge density? You are creating the charge density. Well, of course, for an arbitrary charge density, we won't be able to solve it in the class. So that's why we are not discussing such examples. Okay, so I'll see you after 10 minutes.